right now, your car's anti-lock brakes, the smartphone in your pocket, and honestly, the servers routing this very audio are all being completely controlled by a piece of software designed in the 1970s.
Yeah, it's kind of wild to think about.
It really is. We're talking about a tool built for computers that had less memory than a modern smart light bulb. So today we are taking a deep dive into the invisible foundation of the digital world around you. We're talking about the C programming language.
Which is definitely a topic that touches literally everything we do today.
Exactly. And to understand how a piece of software from the paper tape era still rules the modern world, I want you to picture a desk. It's the late 1970s. Sitting right in the center is a DEC PDP-7 computer.
Oh, those big, hefty, boxy machines, right?
Yeah, exactly. The ones with a front panel just covered in bright, colorful toggle switches. And next to it, there's a monitor glowing with crisp green text. Spilled across the wood surface are these long strips of paper punch tape. And sitting right there in the middle of all of it is a physical, dog-eared copy of a book called the C programming language.
The legendary K&R book.
You know it. Okay, let's unpack this. Because the central paradox we're looking at today is how a language built out of total hardware constraint somehow became the uncontested monopoly of modern computing.
It is a remarkable contradiction.
Yeah.
And, to make sense of it, we really have to recognize that the history we have in our sources here, it isn't just some dry technical timeline.
Right.
This is fundamentally a story about profound human frustration. It's about hitting the absolute physical limits of hardware and the desperate, obsessive quest that these engineers went on to achieve perfect hardware portability.
Well, to understand why a highly portable language like C was desperately needed in the first place, we actually have to go backward and look at what was lost.
Yeah, the dark ages of early programming.
Right. The sources trace this incredible lineage of early programming languages that were just trying to bridge the gap between human thought and machine logic. So in 1960, you had ALGOL 60.
Highly influential, but simply too abstract for writing efficient system software.
Exactly. It didn't get close enough to the physical machine. Then, around 1963, researchers built CPL, the combined programming language. That was massively overambitious.
It was just too complex for compilers of that era to actually handle. I mean, they were choking on it.
So Martin Richards recognized that complexity and stripped CPL down in 1967 to create BCPL.
Right, which was a much leaner, much more practical language. It was designed specifically for writing system software.
And from there, a brilliant researcher at Bell Labs named Ken Thompson took BCPL and distilled it even further into this ultra-lean language he just called B.
But the context for why Thompson needed to invent B in the first place is the real catalyst here.
Yeah, this is where it gets dramatic.
It really does. Because it all stems from the massive, bloated failure of a project called Multics.
The Multics project. So this started in 1965 with Bell Labs teaming up with MIT and General Electric.
A powerhouse collaboration.
You would think so. The goal was to build a time-sharing utility that could serve hundreds of users simultaneously. Conceptually, I mean, it sounds like the dream of the modern cloud, right?
It was incredibly forward-thinking, but they were writing it in a language called PLI.
Which was notoriously bloated and really difficult to compile. The project essentially just collapsed under the sheer weight of its own ambition. By 1969, Bell Labs had seen enough, and they pulled out entirely.
And that withdrawal was devastating for engineers like Ken Thompson and Dennis Ritchie.
Yeah.
I mean, they had spent years growing completely accustomed to the interactive, time-sharing environment of Multics.
They were used to the future.
Exactly. When Bell Labs pulled the plug, these engineers were violently forced backward in time. They had to return to submitting batch jobs on paper cards to a monolithic mainframe.
Oh, man.
You have to imagine the physical reality of that. You write your code by punching physical holes in cardboard.
Yeah.
You hand a stack of those cards to a computer operator.
And then you just wait. Right.
Yeah, you wait 24 hours just to find out you missed a single punctuation mark and the whole thing failed.
Whoa.
The agonizing frustration of knowing how computing should feel and being handed a stack of paper cards instead, it was immense.
And that frustration leads to, honestly, one of my favorite details in this entire deep dive, because Ken Thompson had written this simulation game called Space Travel on the old Multics system.
Classic engineer move.
Yeah.
Writing a game on a massive mainframe.
Right. You flew a spacecraft around a solar system, balancing orbital mechanics, and he desperately wanted to keep playing it after Multics died.
So what does he do?
He finds an underused, virtually obsolete DEC PDP-7 computer just sitting in a corner at Bell Labs. But to get the game to run on this abandoned machine, he had to build a graphics package, an assembler, a rudimentary file system.
All from scratch.
From scratch. And eventually, a core operating system kernel, all directly in the raw assembly language of that specific PDP-7. Wait, so bootstrapping, the first functioning version of the Unix operating system, was essentially like building an entire functioning spaceship out of junkyard scraps just so you could have a place to play a video game.
What's fascinating here is how that exact recreational necessity inadvertently drove one of the greatest leaps in computer science.
Because he didn't want to keep writing in assembly.
Exactly. Maintaining an entire operating system in raw assembly language is incredibly tedious. Because assembly language isn't portable. It is the literal, specific instruction set of one physical microchip.
So it only speaks to that one machine.
Right. If you want to move your operating system to a different computer, you have to rewrite the entire thing from scratch in a new dialect. Thompson and his team realized that to make their new Unix system survive, they desperately needed a higher-level language that could abstract away the specific hardware.
And that was the entire motivation behind Thompson creating the B's language.
Yep. But the hardware landscape was shifting right beneath their feet.
It always does. B was great for avoiding raw assembly, but it had a very specific structural limitation. The sources describe B as a typeless language, meaning it treated all data as a single, uniform machine word.
And just to clarify, that mechanism of machine word is simply the default fixed-size chunk of data a processor bites off and processes at one time.
All right.
The old PDP-7 had a word-addressable architecture. It only knew how to take massive bytes. Because B was designed on that machine, treating everything as a giant uniform block of data worked perfectly fine.
But then Bell Labs acquired the newer DEC PDP-11, and the PDP-11 fundamentally changed how a computer's memory was physically addressed.
It introduced byte-addressable memory.
Right. Instead of only reading massive uniform blocks, the hardware could now process information in much smaller, discrete chunks called bytes.
The PDP-11 could take tiny, precise nibbles, but the B language lacked the vocabulary to utilize that advanced hardware capability.
Okay, let's use an analogy to visualize this hardware collision. Because trying to use typeless B on a byte-addressable PDP-11 sounds like having a massive filing cabinet where you're only allowed to open whole drawers at a time.
Oh, that's a good way to look at it.
Yeah, like even if you just want to look at one single index card, like one character of text, you still have to yank the entire heavy drawer out and take up the whole desk.
The massive waste of physical space and processing energy.
Right. Using a $100 bill to buy a 5-cent piece of candy, and the store isn't allowed to give you change, you're just wasting massive amounts of space.
And Dennis Ritchie saw that exact inefficiency. So he stepped in to bridge the architectural gap. He initiated a transitional phase, heavily modifying B into what was briefly known as New B, or NB.
Adding a bit of nuance to it.
Exactly. The biggest change was grafting a rudimentary type system onto the language. He introduced the char type, which told the compiler to handle single-byte characters, and the int type for standard, larger machine words.
So for the first time, the software actually understood that different variables required entirely different physical amounts of memory.
Yes, that was the stepping stone. But the actual breakthrough, the moment it transformed into what we now know as C, happened when Ritchie introduced structs and arrays, which let programmers group related data together.
And crucially, the sources emphasize that he formalized pointers. But wait, I'm stuck on pointers. The text says a pointer references a physical memory address.
Right, the exact location on the chip.
But why does a programmer writing high-level software need to know the literal physical location of a piece of data?
Think about efficiency. If you have a massive data structure, say, a complex user profile with thousands of attributes, and you want a different part of your program to do something with that profile, copying all that data and moving it over is incredibly slow.
It bogs the whole system down.
Exactly. A pointer avoids that completely. Instead of copying the treasure, you just hand the program a treasure map.
Ah, I see.
You give it the exact coordinate in the physical memory where the data already lives. It gives the programmer the surgical, raw control of assembly language, but wrapped in the readable, logical structure of a high-level language.
That makes total sense. And by 1973, these additions were so powerful and transformative that NB was officially renamed C.
And now, armed with this surgical tool, Thompson and Ritchie did something completely audacious.
The great rewrite of 1973.
Yes. They rewrote the entire Unix version 4 kernel out of raw assembly and entirely into C. Before this moment, Operating systems were exclusively written in raw assembly just to guarantee they ran fast enough.
So they essentially decoupled an entire operating system from the specific hardware of the PDP-11.
The paradigm shift is difficult to overstate. Suddenly, if you wanted to run Unix on a completely different computer architecture, you didn't have to rewrite the entire operating system from scratch.
You just had to write a new C compiler for that specific machine.
Exactly. The compiler would act as the translator, taking the universal C code of Unix and turning it into the specific assembly dialect of the new machine.
That is the essence of the close-to-the-metal philosophy we hear so much about. C implicitly trusted the programmer. It gave them unhindered access to memory without the computational drag of built-in safety nets or guardrails.
Raw power.
And that raw power led to massive popularity, which brings us back to that physical book sitting on our retro desk. Brian Kernighan and Dennis Ritchie's The C Programming Language, published in 1978, it became universally known as KNRC.
Because there was no official centralized governing body dictating the rules of the language at that time, that slim, practical tutorial essentially became the undisputed technical standard for software developers everywhere.
But wait, you're telling me that before official standards existed, an entire global software industry just implicitly agreed to base all their compilers off one slim, informal tutorial book? Isn't that a recipe for total chaos? Because when you look at the quirks of early KNRC, the sources show how chaotic it was. For example, if a developer didn't explicitly specify what type of data a function was supposed to return, the compiler would just blindly assume it was an integer.
Yep. And the implicit int rule.
Or how function parameters were declared on entirely separate lines below the header. It sounds incredibly loose and dangerous for foundational software.
If we connect this to the bigger picture, in 1978, the industry needed exactly that level of flexible common ground to foster a massive explosion in software development.
So the looseness was a feature, not a bug.
At the time, yes. The loose syntax lowered the barrier to entry. However, as C's popularity exploded into the 1980s, you were entirely correct that informal gentleman's agreement completely broke down.
The compiler fragmentation era. You had developers writing code for an IBM PC using vendor-specific extensions that a compiler for a VX mainframe simply couldn't understand.
Right, everyone was adding their own custom flavors.
If companies are inventing their own secret custom rules that Kernighan and Ritchie never wrote down, the original promise of hardware portability fractures completely.
A program written on a Tuesday for an IBM machine was completely illegible to a VX machine on Wednesday. The situation degraded so rapidly that the American National Standards Institute had to intervene just to stop the bleeding.
The ANSI committee.
Right. In 1983, they formed the X3J11 committee. Their mandate was to establish a comprehensive, unambiguous, machine-independent definition of C.
So what does this all mean for the developers at the time? Modifying a language while millions of people are actively using it sounds like trying to rebuild the engine of a commercial airplane while it's cruising at 30,000 feet. How did they not break the internet?
It required a meticulous balancing act between adding structural safety and preserving legacy compatibility. When they finally released the ANSI C standard in 1989, often called C89, they solved some massive systemic issues. One major addition was mandating function prototypes.
Meaning the compiler could strictly verify the number and type of arguments being passed before it even tried to run the software?
Exactly.
Before this, if a program asked a function to add two numbers together and you accidentally sent it the letter A, the system might just try to guess the math or it would entirely crash. AMSIC forced the compiler to proofread the logic first.
They also formally adopted the void keyword for functions that intentionally return no value, eliminating that dangerous guesswork of implicitly assuming everything was an integer.
Oh, that makes sense.
And critically, they established a universal standard library. Operations like opening a file on a hard drive or allocating memory now worked identically on every compliant machine globally, whether it was an IBM, a VAX, or a Mac.
And the language hasn't stopped adapting to hardware since. C99, at the turn of the millennium, introduced inline functions for faster execution, and the standard integer header, to guarantee a 32-bit integer, behaves the exact same way on any platform.
And then hardware manufacturers started hitting a wall.
Right, with CPU clock speeds. They couldn't make a single processor core any faster, so they started gluing multiple cores together.
The multi-core revolution completely broke how software accessed memory, which necessitated the C11 standard in 2011. C11 introduced native multi-threading support and atomic operations directly into the language.
Wait, atomic operation?
Yeah, to understand an atomic operation, imagine two separate processor cores trying to change the exact same piece of data at the exact same microsecond. Without coordination, the data gets scrambled and corrupted.
Like two people trying to write on the same line of a notebook at the same time.
Exactly. An atomic operation essentially locks the door to that memory space while one core is making a change, ensuring the other core awaits its turn.
And looking at the most recent updates like C17 and the newly anticipated C23, the focus has shifted drastically towards security. They are actively pruning the dangerous habits of the 1970s, aggressively deprecating old K and R syntax remnants to catch human mistakes before the software compiles.
Which brings us to the profound legacy of C. Its syntax became the foundational blueprint for the next 50 years of software engineering.
Because everyone already knew it.
Right. When new programming paradigms emerged, language designers didn't reinvent the wheel. C++, Objective-C, Java, they all fundamentally adopted C's syntax, its curly braces, its control structures. By utilizing that familiar logic, millions of programmers could adapt to new, powerful languages almost instantly.
It essentially became the universal language of computing, and its dominance in core systems today remains absolutely uncontested. If you look at the underlying kernels of Windows, macOS, or Linux, they are built heavily on C.
Oh, definitely.
If you look at deeply embedded systems, the invisible microchips firing your car's airbags, pacing a human heart, or steering an interplanetary robotic rover, they are running C. The raw, brutal efficiency is simply unmatched.
But that brutal efficiency is exactly what has created the biggest crisis in modern software.
It's a memory safety crisis.
Yes. That close-to-the-metal philosophy from 1973, the design that implicitly trusts the programmer with manual memory management, leaves the door wide open for devastating security vulnerabilities.
Let's talk about the mechanics of that danger, because people always mention that C is unsafe. I get that it relies on manual control, but what does that actually look like when it goes wrong? Like, what is a buffer overflow in plain English?
A buffer is just a temporary chunk of memory set aside to hold data. Because C trusts the programmer completely, it doesn't automatically check the size of the data going in. A buffer overflow is like having an 8-ounce cup and trying to pour 10 ounces of water into it.
Right.
In a safer language, the system stops you. In C, it lets you keep pouring. The extra 2 ounces spill out of the cup and flood onto whatever is sitting next to it.
Oh, wow.
In computing, that means the excess data spills into adjacent memory slots, overwriting other vital instructions or passwords. Hackers use this exact mechanism to inject malicious code into the overflow space, taking complete control of the system.
It sounds like C is the ultimate Formula One race car. It has unmatched, brutal speed, but absolutely no seatbelts or airbags. If you make a mistake, the crash is spectacular.
This raises an important question for the entire tech industry. In an age of incredibly sophisticated automated cyber attacks, is raw manual efficiency still worth the catastrophic risk of human error?
And we're starting to see serious challengers emerge, right? Like the Rust programming language. Rust is designed to enforce strict automated memory safety rules before the code is ever allowed to run, eliminating those buffer overflows by design.
Rust is making vital inroads, particularly in new, high-stakes system development.
Yeah.
But Rust is fighting an uphill battle against billions of lines of legacy C code.
Because it's everywhere.
C remains a permanent cornerstone. You simply cannot rewrite the foundation of the global digital world overnight.
It really puts our entire digital existence into perspective. We've traced how a language born out of pure frustration, literally because Ken Thompson lost his time-sharing environment and just wanted a way to run his space video game on a discarded computer, ultimately became the undisputed bedrock of your digital life.
The irony is amazing.
It is. Every time you swipe your phone, every time your car's brakes engage precisely when you need them to, you are relying on the logic conceived on that retro desk in the 1970s.
It is a testament to the enduring power of granting developers absolute control, even with all the inherent architectural risks that level of control brings.
And that leaves us with a final thought to mull over. C was invented because developers in the 1970s desperately needed absolute manual control to squeeze every single drop of performance out of incredibly weak, highly limited physical hardware. But as we look to the horizon, as we enter an era of quantum computing and near limitless hardware processing power, will that close-to-the-metal philosophy eventually become completely obsolete? Or, deep down in the architecture, will we always need a way to speak the raw, unpolished truth directly to the machine? Think back to that glowing green text on the PDP-11 monitor and all those paper tapes. The foundation is still there, holding everything up. Thank you for joining us on this deep dive, and keep questioning the digital architecture all around you.